Now, probably the one concept that is most central to all of science, the one topic that transcends through and unites all scientific disciplines, the one thing that no field of science can get away from is energy. The combination of energy and matter makes up the entire universe. Matter is substance, it's the stuff of the universe. Matter is anything with mass and volume. And energy is the mover of substance. While matter is pretty easy to define, energy is a little bit more abstract. That's because energy is both a thing and a process. This is similar to like a word being both a noun and a verb. Persons, places, and things have energy, but we usually observe energy only when it is being transferred from one object to another or transformed from one kind to another. Energy comes to us in the form of electromagnetic waves from the sun. We feel it as thermal energy. It's captured by plants and binds molecules of matter together. It's in the foods we eat, and we receive it, we get it through digestion. Even matter itself is condensed, bottled up energy, which that's the whole meaning behind Einstein's famous formula of E equals mc squared. Our goal in this chapter is to come to an understanding of energy and how it's transferred and transformed. In this video, we'll begin our learning about energy by looking at two related topics, work and power. We'll see how these are related to energy as we go along. By the end of this video, you should be able to define work and power from a physics perspective, compare the amount of work done between two or more objects, state the conditions when no work is done, calculate the amount of work done on an object, and calculate the power generated by an object, and explain what it means to be more or less powerful. So, let's get started. So when we talked about momentum in the last chapter, we saw how that changes in an object's motion depend on the force applied to the object and the amount of time that that force acts. We called this quantity, force times time, impulse. But the term how long does not always mean time. It can also mean distance. So when we consider the concept of force and distance, we're really talking about an entirely different concept called work. So if you were to push a crate across the floor, work is done on the crate. So we say that we do work on the crate. The heavier the crate, the harder you have to push, so the more work that's done. Similarly, if you push the crate a longer distance, you do more work. So two things enter the picture whenever work is done. First is the application of a force, and second is the movement of something by that force. For the simplest case, where the force is constant and the motion is in a straight line in the direction of the force, we define the work done on an object by an applied force as the product of the force and the distance through which that object is moved. So in shorter form, work equals force times distance, or work W equals FD. So say you were to lift two identical objects up one story. You would do twice as much work as you would do in lifting the same load up one story, because the force needed to lift the weight is twice as much. Similarly, if you lift just one of those objects up 2 stories instead of 1 story, you would do twice as much work because the distance is twice as great. Now, because the definition of work is force times distance, this tells us that if the distance an object is moved is 0, then no work is done, even if a force acts on an object. To understand this, imagine you push as hard as you can on a wall. You exert a force on the wall, but the wall does not move. Therefore, you don't do no work on that wall, even if you stand there and push for a long time. Now, while it might be true that work is done on your muscles by stretching and contracting, which is the force times distance on a biological scale, this work is not done on the wall. So, if an object does not move, no work is done. Also, if the force that's being applied and the displacement are perpendicular, in that case, no work is done. Like this case here, we've got a person carrying a suitcase. They're pulling up on the suitcase while walking forward. This object, the suitcase, does not move in a vertical direction, okay? It only moves in this horizontal direction. Well, the force that's being applied is in a vertical direction. That force and displacement are perpendicular, therefore no work is done. So work generally falls into two categories. First, the work done against another force. Second, the work done to change the speed of an object. And here are some examples of this first category of work. Say when an archer pulls back on a bowstring, she's doing work against the elastic forces of the bow. Or when a ram, the ram of a pile driver lifts up, when it's raised up, work is required to raise that ram against the force of gravity. Or when you do push-ups, you are doing work against the force of gravity, or of pulling you down, okay? So you're doing work against your own weight. When you do work on something, when you force it to move against the influence of an opposing force, that opposing force is often friction. An example of the second category would be like anytime you're causing a car to speed up or slow down, you're changing the speed of it, there's work that's done to change the speed of that object. Now we need to keep in mind that in both of these categories, each involves the transfer of energy, which we're going to take a closer look at later, but these are the two categories of work. Now when we go to calculate work, we're going to put it into its correct units. The unit of measurement for work combines the unit of force, the Newton, with the unit of distance, the meter, to give us this Newton meter. Now it's more common to take this, instead of measuring work in Newton meters, we measure it in what's called joules. So 1 joule of work is done when a force of 1 Newton is exerted over a distance of 1 meter, as in like lifting an apple over your head. For larger values, we speak of kilojoules, which would be thousands of joules, or megajoules, which would be millions of joules. So like a weightlifter would do work in kilojoules, or to stop a loaded truck that's moving at 100 kilometers an hour takes megajoules of work. Okay, so let's move on now and take a look at power. Now the definition of work says nothing about how much time it takes to do the work. So whenever we ask about how much time something takes, we're talking about a rate, okay? Now, the same amount of work is done when you go up a flight of stairs, whether you walk up the flight of stairs or whether you run up the flight of stairs. That's because you're moving the same load, up the same distance, the stairs. So the same amount of work is done, whether you run up the stairs or whether you walk up the stairs. So why are we more tired after running up the stairs than we are after walking up the stairs? To understand this, we need to talk about a measure of the rate at which work is done. We call the rate at which work is done power. So power is the amount of work that's done divided by the time interval that it takes to do that work. A high-power engine does work very fast. An automobile engine that delivers twice the power of another automobile engine does not necessarily produce twice as much work or make a car go twice as fast as the less powerful engine. Twice the power means the engine can do twice the work in the same amount of time, or do the same amount of work in half the time. A more powerful engine can get an automobile up to a given speed in less time than a less powerful engine can. And that's what's really important to understand about power, is that when we're talking about power, we're talking about being able to do work over a certain time interval. If we got a lineman, you might be a lineman. A powerful lineman is both strong and fast, so it applies a big force over a small amount of time. Another way to look at power would be if you take like a liter of fuel. Okay, a liter of fuel can do a certain amount of work, but the power produced when we burn it can be any amount, depending on how fast it's burned. It can operate, 1 liter of fuel can operate a lawnmower for a half an hour, or a jet engine for a half a second. Now the unit of power If work is measured in joules and time is measured in seconds, that would make the unit of power a joule second. And we call a joule second, 1 joule second per second is 1 watt. So 1 watt of power is expended when 1 joule of work is done in 1 second. 1 kilowatt equals 1,000 watts. 1 megawatt equals 1,000,000 watts. In the United States, we customarily rate engines in units of horsepower and electricity in units of kilowatts, but either may be used. In the metric system of units, automobiles are rated in kilowatts. 1 horsepower, by the way, is the same as 3/4 of a kilowatt. So an engine rated at 134 horsepower is a 100 kilowatt engine. Okay, so we're going to take a look at examples of power. We're going to do an activity on power in class and move that later in the next video into energy. See you then.